Modern AI infrastructure relies on millions of standardized components from dozens of different vendors. The servers, switches, and storage arrays all speak the same syntactic protocols, allowing them to link together physically. But at the boundaries between these independently optimized systems, the coordination breaks down. Engineers call this boundary waste. A storage cluster might optimize its own internal read speeds, completely unaware that the GPU requesting that data is already stalled. The individual components meet their local specifications, but they fail to communicate their operational intent to the rest of the dependency graph. Consider a distributed training run. If a network fabric detects local congestion, it might adapt by briefly pausing traffic. Locally, the fabric is operating perfectly, but that microsecond pause can cause a massive distributed checkpoint to stall across thousands of GPUs, destroying the entire workload's time to first token metric. This chart compares three models. On the left, vendor-integrated stacks eliminate waste through shared telemetry and a single control loop. The middle panel, representing the open stack, suffers from semantic gaps. Open standards lack the coordination required to guarantee an end-to-end result. Open standard infrastructure cannot close this performance gap simply by building faster individual chips or wider network links. To compete with heavily integrated vendor platforms, open systems require a unified outcome coordination layer. The Predictive Tensor Control Plane, or PTCP, is a proposed framework designed to bridge that exact semantic gap. It does not replace open standards like Ethernet or PCIe. Instead, it sits above them, translating application requirements into a unified control signal. The core mechanism of PTCP is the AI quality of service contract. Rather than tracking disjointed metrics like packet loss or CPU temperature, an AIQoS contract declares a single accepted workload outcome across the entire dependency graph, like the successful delivery of an interactive inference token. This animated equation breaks down how PTCP calculates value over a specific time window. It multiplies the intrinsic value of the work unit, labeled here as V sub I, by a strict constraint variable, A sub I. That variable, A sub I, is entirely binary. It only equals 1 if the system perfectly meets every condition, like latency deadlines and token volume. But if it violates a single security boundary or freshness constraint, the variable drops to 0. The accepted value of the work instantly shatters. Defining success as a strict binary condition prevents subsystems from gaming operational metrics. A network controller can no longer claim high average throughput if the packets arrive too late for the GPU to use them. Dropped requests and retries count as zeros. By enforcing a hard mathematical constraint on the final accepted outcome, PTCP forces every underlying infrastructure component, from the storage arrays to the cooling systems, to align directly with the application's actual success criteria. Attempting to run a single, centralized real-time controller across a heterogeneous network, from the data center core to the mobile edge, is an architectural impossibility. The latency is too high and the state changes are too rapid. PTCP resolves this by acting exclusively as a slower, predictive supervisor. It seeds microsecond-level reactions to the native fast-loop controllers. Switch buffering, memory coherence, and TCP congestion response remain fully authoritative within their local domains. This flowchart illustrates the PTCP processing pipeline, mapping the supervisory loop from data ingestion down to policy execution. Across the top row, the system ingests a continuous stream of telemetry. It normalizes data across vastly different domains, pulling state not just from CPU and GPU usage, but factoring in cache health, power draw, and identity verification. After forecasting risk, the policy compiler in the middle row translates the findings into specific actions. Crucially, these are not direct hardware commands. PTCP issues bounded, signed, and leased action envelopes back to the native schedulers and NICs, providing strict boundaries for local execution. Separating timescales allows the architecture to predict and route around cross-domain saturation before it occurs, without ever interfering with the microsecond hardware reactions keeping the system stable. Tracking the joint state of every single variable in an AI factory creates a massive data density problem. Cross-referencing every queue depth, temperature sensor, and memory state simultaneously generates an exponential dimensionality that no system can compute in real time. To compress this data into something computationally useful, PTCP utilizes Pattern-of-Life Tensor Train decomposition. This diagram shows how that math works in practice. On the left, the dense joint state scales exponentially. On the right, the tensor train framework factorizes that massive array into a sequence of smaller, mathematically manageable cores, labeled G1 through G4. Notice the explicit condition at the bottom. This only works when tensor ranks remain moderate. Data center telemetry exhibits highly correlated, repetitive behavior. That inherent structural pattern is what makes this extreme compression mathematically possible. Once the system learns the baseline pattern of life, it monitors incoming telemetry. Any deviation from the factorized tensor cores generates an anomaly score, immediately flagging structurally abnormal behavior across the network. A traditional dense histogram requires too much memory to hold this many variables, and unbounded neural forecasters consume too much compute and introduce unacceptable lag. Advanced tensor mathematics is the absolute prerequisite for tracking hyperscale cross-domain telemetry. Without it, the infrastructure cannot detect complex failure states until after they saturate the network. Tracking network state is only a prerequisite. The controller's actual objective is to issue routing policies that strictly minimize operational tail risk. To achieve this, PTCP calculates conditional value at risk. Instead of optimizing for average performance, which can hide rare but catastrophic events, the math heavily penalizes forecast shortfalls, actively calculating the risk of gray network failures or collective checkpoint collisions. PTCP uses these risk penalties to map what it calls geodesic networking paths. A geodesic path here isn't the literal shortest physical route. It represents the safest admissible route based entirely on the calculated risk of failure. This schematic maps how security protocols integrate into that risk calculation. It contrasts a standard green geodesic path against a red topological cage. When PTCP detects a zero-day structural anomaly at node D, it calculates the smallest enforceable cut to isolate the threat. The red topological cage mathematically constrains the blast radius by reducing unauthorized reachability. Simultaneously, the geodesic path automatically routes the remaining authorized traffic around the cage. Critical AI service paths remain explicitly protected and functional, maintaining good put even while a containment event is active. Under this control plane, security and performance are no longer separate, conflicting operational silos. They function as mathematically unified constraints within the exact same routing equation. Modern AI workflows rarely exist entirely within a single facility. They span from the core training data center out to telco networks and physical edge devices. To scale across boundaries, PTCP utilizes a federated architecture. As mapped here, regional domains feed into a unified coordination layer. They exchange capability forecasts, never raw data. The text below outlines disconnected operations. Edge nodes cache local policies. If disconnected, they must be capable of autonomous operation. This enforces a principle of asymmetric enforcement. An overarching AIQoS objective, such as a strict perception-to-action deadline, remains identical whether the target hardware is an open Linux server or a locked-down smartphone. The adapter simply compiles the policy using only the controls that specific endpoint exposes. The system relies on a fail-native fallback protocol. If a PTCP lease expires or a cross-domain controller conflict occurs, the endpoint instantly and safely reverts back to its proprietary local schedulers. True macro-architectural resilience requires designing for intermittent connectivity and structurally trusting local systems to survive on their own when the broader network fails. At this stage, PTCP is a structurally coherent hypothesis. It requires rigorous, multi-arm A/B testing against highly optimized native controls before any of its efficiencies can be claimed as fact. This diagram outlines the sequential integration program required to prove PTCP's efficacy. The system begins at Step 2, running in a shadow mode forecasting risk without taking action. After proving predictive accuracy, it advances to Step 4, issuing bounded canary actions under strict safety thresholds. The white paper enforces a strict publication rule for this architecture. No theoretical performance percentage can become a commercial product claim until it is independently reproduced on live hardware. Industry standards have proven they can make hardware components physically substitutable. But the ultimate market value of PTCP lies in its potential to take those fragmented parts and finally make the end-to-end AI outcome guaranteed, efficient, and entirely portable.